Okay, so let's come back to our class, our discussion for the PD and PFA. So I think this example at the beginning it looks simple, right? You have no signal and you have a signal. It looks simple. Now, and yet, after we do the mathematics, it doesn't look very simple, right? It doesn't look as simple as we thought at the beginning. So now you start to get a better understanding of a couple points. The first thing is a detection problem. While it looks simple, the mathematics behind it, the theory behind it may not be that simple. The second thing is you sort of need to understand there is a systematic way of dealing with this problem. Recall that at the chapter 1 and chapter 2, when we talk about a detection problem, we always say one half seems to be the best, right? You set a threshold, for example, let's go to 64. We see this figure. We will set a threshold here at the middle of the intersection, and then we will say, okay, that seems to be reasonable, and then the business is over. Now you start to see that it's not that simple, right? We have a simple problem to start with, and then at the end of the day, it doesn't look that simple. We have to calculate a lot of things just to satisfy some property, and also you need a systematic way to deal with it. Not just say, okay, I set a threshold here, I set a threshold there, and then the business is down. No, no way. It's not that simple. The reason we need to do that is in engineering problems, we usually have a lot of requirements. For example, if we are doing communications, we are concerned about the error rate, right? We put a very strict standard on the error rate. An error rate of 10 to the minus 3 is no good. We like it to be 10 to the minus 4, 10 to the minus 5, or even less, right? In image processing problems, we also like to be accurate, right? For example, in facial recognition, you know, there are there are 20 million people in Taiwan. If you like to do a facial recognition, you like to pick one person out of 20 million. You you know, one person out of 20 million. So how accurate would it need to be? It has to be very accurate, right? So those are all detection problems, and some of the requirements are actually very high. It comes from the practical considerations. It's not mathematics only, right? So okay, so let's come back. So we are related this to this more directly by noting that Q function is monotonically decreasing since 1 minus Q is a CDF, which is monotonically increasing. That's Q has an inverse that we denote as Q inverse. As a result, the threshold is found from 3.6 as something like this. Right? Go back a little bit. We're looking at 68. Now you have a Q of this as PFA. Then you can take the inverse function, right? Take the inverse function of this and then take the inverse here. So now you have gamma prime equal to square root of this. This is, of course, coming from here, this whole thing. Simplification, and then you get a inverse version of the gamma prime. Alright, now you take a look at PD. PD has gamma prime, but gamma prime is now a function of PFA. As a result, we can build a relationship between PD and PFA. Right? PD and PFA, we can build a relationship. Now PD is equal to Q of this thing. Because of what? Because we replace the gamma prime with this function of PFA. So now you don't see gamma prime here. You see PFA here. And then PD is now a function of gamma prime, but also a function of PFA. You do some simplification, this and this cancel out, and this combined, we get this. So you have Q of Q minus 1, this and this. So now you have a PD versus PFA, right? PD. All the rest is what? Parameters. A is parameter. Sigma squared is parameter. N is a parameter. So now you have a PD. You have a PD. You have a PFA. So now you have a PD here. You have a P. Let me see. Let me make a correction. I'm saying PD as a function of this thing. You can see it as a function of PFA, which we will talk about later. But now this figure is doing PD versus this. And this has special meanings. This has special meaning. Just to make it easier for you to follow, we are looking at page 69. Okay, so this has one meaning. Notice that this is a probability of detection. While PFA is not decided yet, so it has to be given a specific PFA, then you have a PD versus this, right? You have a PD versus this for a given PFA. So when the PFA is this, and you have a PD versus this as this. When you have a PFA this, you have a PD versus this as this. You have a PD versus this for given PFA, so on and so forth, so you get a sequence of curves. But this thing has special meanings because as you see, you have samples here, you have A here. So what that means is this is actually the signal energy. Conceptually, I'm saying conceptually，在观念上来讲，这一个像就是讯号的能量。好，因为它跟这个数目有关，它跟数目，你想想看哦，如果你 take 越多 sample，是不是代表你取得越多讯号的能量，对吧？好，那如果 A 越大，是不是代表讯号的能量也越大，是吧？好，那 sigma square 是什么呢？sigma square 就是 noise 的能量。所以我们会把这样子的东西在观念上称之为讯号除以能量，讯号的能量除以杂讯能量，所以我们就把它称为是讯杂比。讯杂比。So we will call this as energy to noise ratio. Sometimes we call it signal to noise ratio. Sometimes we also call it SNR. 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 Signal to noise ratio. We call it signal to noise ratio. Okay, SNR. 所以 okay, so this is sort of a PD versus SNR. And then as you see, if you have more signal energy, you have better PD, right? You have less noise energy. You also have larger value of this, so you also have better PD. But you can look at it in different directions. You see, PFA, you have a larger PFA, then you have worst. Oh no. You have better PFA, meaning the less PFA, then you have better PD. You have worse PD，就是 PFA 越小，代表 PFA 越好，那你的 PD 就越小。这跟我们先前谈到的那个 trade off 是不是一致的嘛？对吧？一致的，就是你 PFA 跟 PD 是一个 trade off 这样子。Okay, so that's the criteria, the P, the you see here with the signal energy to noise ratio. Then of course you can write it in this is what this is like log scale. So you have a you make it into a curve, into a like a straight line. But it's just a change of the scale. Change of the scale. And okay, we'll skip some paragraph for you for your own reading. Okay, fine. I'm just pointing out some of the main points. This is a mean shifted Gaussian problem. On the H0, it has a specific mean here. It has a mean. On the H1, it has a different mean. But the sigma square are the same, so it's mean shifted. Mean shifted. Okay. So the detection performance of this mean shifted problem is totally characterized by the diffraction coefficient d squared and defined this way. It's e of this minus e of this square over variance of t conditional h0. So it will be mu1 minus mu0 over sigma square. In the case when mu1 is 0, then it will be like that. It will be interpreted as a signal to noise ratio. To verify the dependence of detection performance on d square, we do some mathematics derivations. Then you see PFA is something like this, which we did before. PD, we go through this step by step, we get this. Then now using 3.9, this. We see you have something here, right? You have something here, which is identical to this term, except there are some squares. Okay, then use 3.9 and we have PD equal to something like this. As a result, you see PD is related to this d squared, the diffraction coefficient. Okay, then there are other types of problem, for example, change invariance and so on and so forth. We'll leave it to your own exercise, and some of them will be in homework. So, yeah. So now let's skip some paragraphs. You see that there are DC level in non-Gaussian noise, non-Gaussian. Non-Gaussian is a bit more complicated. Alright. So now we go to this receiver operating characteristic. We have talked about PD, PFA, and some examples. And an alternative way of summarizing the detection performance of an NP detector is to plot PD versus PFA, which is something like this. PD versus PFA. As an example, for the DC level in WGN, we have from this PFA equal to this, right? We did it. And we have PD with respect to this. and PT to this, which we all did. So not a problem here. Okay, so uh, now we see that one of the parameter to be adjusted is the gamma square. If we adjust, excuse me, the gamma prime. If the gamma prime is adjusted, then the PFA will be adjusted, and then PD will be adjusted, right? So, in other words, what we can do here is we can adjust the threshold in the detector to change PFA and PD. So, uh, then there comes a problem, which is uh, how do you get an overview of the detector? Because different gamma prime will give you different value of PFA and different value of PD, right? So it's hard to say which is better and which is not, which is worse, right? So we find a way to summarize this detector. So this type of performance summary is called receiver operating characteristic. Again, this is very important. I want you to remember this because uh, whenever you encounter a binary detection problem, you need to talk about the receiver operating curve. Otherwise, your discussion will be insufficient. You can set a threshold and say you have good performance, but without ROC, you don't get a summary of the performance. All right, so the ROC is a function, is a curve, is a curve. What curve? It's a curve of PD versus PFA. It's a it's a it's a curve. What curve? And here is PD. Here is PFA. So you get a PD versus PFA. And of course, then we see it here, right? We see it here. We see it in many places where we have PD as a function of PFA. So you will see a curve like this. You will see a curve like this, right? That's a PD of versus PFA. And then it's always above the 45, 45 degree. This is because the 45 degree can be attained by a detector that makes a random decision. If you just make random decision, you don't have any information, then you get a 45 degree. You get a curve like this. You get a curve like this. You get a curve like uh 45 degree. You get a 45. That's a random guess. So that's a flipping a coin, ignoring the data. Right. Consider a detector that comes up with a head, and we have something like this. We have conditional H0 is a head or conditional H1 is a head, and of course then under this kind of detector, what would you get? You're actually getting this 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 curve, right? And so did you have PD versus PFA, and what's the PD versus PFA is you like PFA to be small, you like PD to be large. So as a result, the so-called good detector will always look like this. If it goes up here and here, it's better, right? Here and here. The optimal detector will be something like it goes from here up to here and then goes to here. Why? Because you like PFA to be 0, PD to be 1. That would be perfect. That would be perfect. But usually we don't get detector like that. So we like to push this ROC up to this point. The closer to here, the better we are. That's the the PD and PFA. Okay, and we call it ROC. Remember the name. Okay, remember the name. And then when you tune the gamma, you tune the gamma. For example, you increase the gamma. Of course, that only applies to the Gaussian cases. You increase the gamma, you are decreasing the PFA. Also, you decrease the PD. Right? There is no free lunch, so you sacrifice PD as a gain to PFA. And then, of course, the other side is you will decrease gamma prime. You go this way. It goes to this way. Okay. Okay. I think uh that's for this session, and then we'll stop for a couple minutes, and we come back.